everyone, I'm Cristina and in this video we look at Thread Local Storage callbacks. Thread Local Storage is a mechanism for Windows applications to execute code which is thread specific, and the interesting thing is that it executes actually before the main function. Here we have a simple C++ application. The main function displays a message box and we defined two TLS callbacks. They are almost identical, with the only difference that the second one also terminates the process. Very straightforward. Finding out how to define them took a bit on online digging, but there are good references, although a bit hidden. Make note of the code here. So, we'll first build the application from Visual Studio, then check its behavior. The first callback is executed and then the second one. But the main function doesn't execute at all. Because of this instruction here, you can probably imagine what opportunities this presents for a malware writer. Imagine someone could add a lot of code inside the main function, which would act as a decoy while the malicious code would execute inside a TLS callback. Since most of us would probably start analyzing from the main function, we could miss the payload. A very nice way to hide your code. But that's not all. Let's see what happens inside a debugger. Let's see with Immunity Debugger. We load the sample and even before running it, both of the callbacks are executed. Strange. The application also quickly terminates without even giving us the chance to set up any breakpoint. This is interesting from an attacker's perspective because one could add some instructions almost hidden. To work around this breakpoint issue, we'll change the debug options under the Events tab. Instead of the default breakpoint at win main function, we want to break at system breakpoint. Restart the sample and see if this setting worked. Yes, the breakpoint worked. Now the execution stops before both of the callbacks. Good. Let's move on and try the same sample in IDA Pro. It tells us that the application has debugging symbols and wants to load the corresponding PDB file. Yes, we do. IDA Pro shows us first the start function, and rightly so because it's the entry point of the application. Set a breakpoint here and start the debugger. Exactly as before, two TLS callbacks and the application terminates before hitting our breakpoint. Let's verify that this is indeed the entry point of the application. For this, we'll open the application in a P-Analyzer tool, for example, CFF Explorer. Inside the optional header, we have the address of entry point, which is 11334, and also very important, the image base, which is 004 and 5 zeros. Copy the address of entry point and go back to IDA. We have the relative address of the entry point, 11334, same as before. But notice the image base has changed after we've terminated the debugging session. Scroll to the top of the assembly code and see here that the new base is now 010E, 4 zeros. So things make sense. Let's compute the new address of the entry point relative to the image base. We'll use the Windows calculator in hex mode. OK. And we get 10F1334. We will jump to this value and we'll write on the entry point. We got the entry point figured out. Great. Back to CFF Explorer. We see something very useful here, the TLS directory section, and in their address of callbacks, which should lead to the user-defined TLS callbacks. This is a very good method to find out if your sample has any TLS callbacks defined. Keep in mind that the image base was already added to it. The value of image base is 00450 as we saw before. So to get the relative address of the callbacks, we subtract the base and get 17720. We copy it and go back to IDA, but remember we have to add the new base, which changed after the debugging session. If I remember correctly, the new image base is 010E40, but let's check. And add that and we get the new virtual address of the TLS callbacks. Copy that and jump to the address. We can press G. As expected, we have the two callbacks we defined in the source before. Each of them is very simple and contains the message box. Another option is to use the function list on the left and search for TLS with Ctrl F. And we have 4 functions, 2 of them are wrappers over the other 2. If you're curious, let's also locate the decoy code of the main function. We'll see that it is not in the start function we've seen before. So what's happening? No message box here. Why? The reason is that C++ applications have a lot of loader-related code that wraps up the main function. We can do another trick, find cross-references to the message box function. Message box gets called from both callbacks here. Let's see all the cross-references. This is the actual code we wrote in the main function. So here's the code. We'll rename it, just for convenience, to actual main. Let's do some more cross-references. We actually have another way to visualize the function called tree, leading to the actual main. we go to View menu, Graphs, and then Xrefs to here. Here we have a nice call hierarchy, starting from the entry point, the start function, and goes down to the actual user-defined main function. Okay, to wrap up, now we know how to detect if an application has any TLS callbacks from the PE header. We also know how to configure Immunity Debugger to break before the callbacks code, which could be malicious, by changing the debugging options. We also know how to correlate information from PE headers with dynamic segments in IDA Pro, right? So thank you very much for watching. If you find this useful, please subscribe to the channel for more videos.